the purpose of the triangle inequality is to compare distances that we know, or distances that we know an upper bound for at least, so distances that we say we can control. Compare distances that we can control to others that we might not know how to control. So in this diagram on the group assignment, there are 6 different real numbers that we don't know, but we happen to know some comparisons, or some upper bounds, I should say, between the distances of some of them. So for example, we don't know the distance from x to y. In fact, that's kind of the point of this problem, is going to be you're going to find an upper bound for the distance between x and y. But we do know, for example, that the distance from x to e can be controlled. And when I say that, what I mean is that we know that the distance between x and e is less than 5. So that's what this little piece on the diagram means. And so the purpose of question number 2 is going to be to use the knowledge of how x and y, the distances from x to y, can be controlled to all these other points, a, b, c, d, and e, right, to discover some upper bound on the distance from x to y. And the simplest example, I'm going to draw one more diagram on this to finish up the argument. Let's suppose that I just have 3 numbers, x, y, and z. And I happen to know that that the distance from x to y, so I'm going to kind of draw this again conceptually, the distance from x to y is less than 3. Okay. And I also know that the distance from y to z is less than 4. Less than 4. And so then the question is, what can I say about the distance from x to z? How far apart can x and z possibly be? Right, the furthest apart that they can possibly be is 7. Right. Now they could be fewer than 7 units apart, right? In fact, let's suppose x were equal to z. Then, in fact, if x minus y, if the distance between x and y is 3, then of course the distance between y and z is less than 4, because in particular it's going to be less than 3. So the distance could be as small as 0, okay, but it cannot be any larger than 7. In fact, it can't even be equal to 7. Why do you think this inequality is called the triangle inequality? Those of you who had me for geometry last semester, you know the answer to this. Why is this called the triangle inequality? What does it have to do with triangles?
Because they form a triangle.
So, right, if we take this notion of absolute value and replace it with distance in the xy plane, for example, right, then what this is saying is that the distance between x and y added to the distance between y and z, so in other words, that would be the distance that would take me from x to y combined with thence taking me from y to z, that distance of going from x to z via the third point y cannot be any shorter than the distance of going directly from x to z. And so in geometry, the statement of the triangle inequality is that the sum of any 2 lengths of sides of a triangle has to be at least as large as the length of the third side. Right? We can't get from x to z any quicker or any shorter by making a stop at y along the way than by going directly. The shortest distance between 2 points is a straight line. That's another colloquial statement of the triangle inequality. So what we find out about the triangle inequality in this packet, though, is that it's not something that's just sort of special to 2-dimensional geometry, that it also works when we think about measuring distances using the absolute value on the real number line. So it's like a 1-dimensional geometry statement, right? But one of the things that you find if you build further into the abstractions of analysis is that this is a statement that's true of any way that we could choose that's coherent in which to measure distance. So even if we decide to measure distance in wacky, crazy ways, the triangle inequality is one of the things that we cannot forsake. Right? Every way of measuring distance that makes any sense as a distance has to satisfy the triangle inequality. Right? So the purpose of this packet is to get you introduced to how to use the triangle inequality in making an argument. And we'll also see in question number 3 that we're going to plug in the Archimedes principle that we talked about from the third packet into this process to help us to use the triangle inequality to begin to make some assertions that are going to be especially important when we think in packet 5 about sequences and what makes a sequence converge.